if you have missed anything, or if you want to go through some more information in detail. So I'm going to stop sharing my screen, and Yoram, I'm going to ask you to share your screen, and then Yoram will go over the presentation and do a live demo with everybody today. We will use our EM scanner, and we will show you some near field probes, the kit that we have. So it should be a very informative session. So thank you very much for joining Innovate. Thank you for arranging it. And yeah, we'll talk to you after Yoram has finished the demonstrations. Thank you.
Thank you, Cornell. Let me share my presentation. Hi, hello, everyone. So first of all, again, thank you for joining. In this presentation, we will speak about Y.I.C, a brief introduction, who we are, where we are operating from, and what we do. Then we will discuss a bit about near-field scanning solutions. We'll discuss about best practice for PCB design to mitigate EMC or potential EMC EMI.
Screen is not visible. Your screen, you're not
sorry.
The screen. You're not sharing the screen.
Okay, I am sharing the screen for some reason. You don't see anything?
I can see.
I can see.
Nanda, can you see?
We are not able to see the screen. I think only I am not able to see. Yeah, other people are able to see.
Yes, it is visible.
Yeah.
Okay.
Please go ahead.
Okay. So I have Cornell here joining as a user. So if there's any problem, she will be able to notice it, and then hopefully everything will run smoothly. So I was saying that we will discuss best practice for PCB design, and then we will see actually live examples. So the live examples, we have few. Let me turn on my pointer here. So we have a few demo boards. We will use two of them to show you guys how potential EMC or potential bad PCB design looks like from EMC perspective. So we have these RFID boards with the RFID antenna, the 13 megahertz, the control circuits, and we have the EDU kit with several different potential issues. So we will scan them and we will see exactly how it looks like. So let's start. Y.I.C technologies. So we are developing EMC EMI scanning solution or diagnostic tools. We are a UK-based company. In the UK office, we are doing essentially the administration and software development, but the manufacturing is still, and hardware development is still being done in Canada from historic reason. I'm Yoram Shimoni. I'm the technical lead for the company regarding this equipment. So I assume if you're here, you all know about EMC, electromagnetic compatibility. You all know why we need it, or what do you need to do in order to actually sell the products. The best way to explain it for people who are not really involved with that is these logos. So any product out there that you see any of these logo, that means it requires some kind of certification before you can sell the product. This is for commercial field. On the medical and aerospace markets, obviously the test is much more significant. Here you can see, for example, the entire helicopters in a chamber. You don't want that part or component within the helicopter, the car, the medical equipment will influence and alter measurements, results, or operation of other nearby component. And essentially, this is the whole idea behind EMC testing. You would like to characterize your product, understand the emission, where they're coming from, and how to mitigate them. Essentially, you want to minimize the potential to interfere with other products. In sometimes it's really, really critical, and in sometimes it's not that critical. But still, there are some international standards that require us to essentially, the manufacturer to confirm to specific EMC requirement. Usually it's been done, sorry, many people are joining in. Okay, so obviously the majority of the test is being done, actually all the test is being done in the far field. It's either 3 meters or 10 meters away from the DUT. Our equipment, or most of the EMC debugging equipment, is actually being used in the near field. So we will discuss a bit the differences and how or why it's actually making sense to use near field equipment to identify potential problems in the far field. And there are many processes and many types of EMC testing. Emission testing, it can be conducted or radiated, and immunity testing. We will focus in this presentation on radiated emission testing. These are the tools that, I mean, our tools can measure the radiation or the emission output from or emitted from your product. So the key focus of the near field testing or scanning equipment is radiated emission. We do have capability to test or to allow the user to test immunity, but keep in mind that we have no visibility into the functionality of the product. We can create some kind of magnetic field around the products that might cause some functionality issues, but we have no way to monitor the functionality of the DUT. This is on the designer or on the manufacturer. So these are the two key issues that we will look into. So far field is not everything. Even though the test or you measure the field created by your product in the far field, it actually depends on frequency. We usually say that far field starts few wavelengths away, 4 to 6 wavelengths away. There is a bit of more sophisticated or complex formula, but usually 4 to 6 wavelength away can be considered a far field. The best way to define it is we say that in the near field, the field still depends on the source and the victim. And in the far field, it's more depends on the medium, air, water. So there's no influence of the source, couplings effects and things like that. However, usually in the near field, if you will measure a specific frequency, it will be visible in the far field as well. And that's essentially the key for debugging in the near field. The key problem in the far field, and I think the next slide explains that, is you only get pass fail. There's no real way to identify the issues. You will get some kind of a number which says, okay, the field is too high, you failed the test. But it will be very difficult to identify the source of the problem. While in the near field testing allowed you to identify the problem and the potential issues actually in a pretty accurate way. In addition, the speed of the test. Usually, near field test requires less setup, less handling. You can do it, from the bench top at your lab. Essentially, there's a lot of advantages working in the near field, and you can get the same idea of the issue in the near field as well. Now, the idea is actually to push the near field testing earlier and earlier into design phase, into the design phase. Not just when you have a prototype ready for EMC EMC testing. Actually, usually most of the companies are doing that on the final product. But the idea is to push the characterization of the emission from your product as early as possible, even to a first prototype. So obviously, most people run simulations, but after that, usually they're waiting for the final version and go to a chamber, and then it fails. Then it causes issues. But if you can characterize the emission as early as possible in this cycle, that will save a lot of money and time. And essentially, this is the whole idea behind affordable, quick, easy to use near field scanning solutions. So as I mentioned, the whole idea behind that is to allow you guys to do essentially in-depth PCB analysis and verification. Things like that, for example, you will not be able to see in the far field. This is only near field scanning. And there's a lot of typical design flows that you can identify in the near field. And then if it's during the prototype, you can easily or essentially with low cost amend the PCB or make the necessary changes to avoid these things on the final product. So most likely during the prototyping, people will start scanning the source, the paths of the current, and the way that current is actually being distributed across the PCB. And here you can see a few examples how energy, for example, coupled into a control line, and that's a big problem. And you will see that later on. That can definitely influence the behavior of the PCB or of the product. Cause I don't know if it's a video thing. You can easily cause bare errors, and if it's encryption or something else, you will see problems even in the digital domain down the road. Pre-production functional verification, again, very easy to identify production issues and actually make yourself ready for the certification process as early as possible in the development stage. Post-production, we use near field scanning to actually fault diagnostics. And you will see that down the presentation. We can verify different types of processors or even dead component. Usually the assumption is if a component operates at a certain frequency, it radiates at that frequency. So it's very, very easy to identify that frequency around the surrounding area of that component. So if you don't see anything and you expect to see something, obviously this component is dead. So since the scan takes essentially a minute, it's a very easy way to identify and diagnose things, a problem. So let's talk about the near field solution. Obviously, there are pros and cons. Let's start from the con. So first of all, I guess you all know the handheld near field probes. It's something like that. You just wave it around the PCB and start measuring the field. It's a handheld device. It's less accurate. It's not repeatable, but it is the most common way. It has a limited special resolution, but actually that should be on the pro slide. But again, the cost of that solution is fairly low. The key issue with handheld solution is the repeatability. A magnetic field is a vector. It depends on the orientation. Your measured value depends on the orientation of the probe. If we are using a non-controlled environment, it will be very difficult to repeat and get consistent, repeatable results. However, it's very cheap and quick solution. The next one is essentially the automated near field scanners, and this is something like that. And this is actually our scanner. So the idea behind it, or again, something like that, that you can easily build yourself today. The advantage here is that it's more controlled environment. You can precisely control the near field probes. However, they're a bit more complex to set up. Most likely you will need some kind of an integrated software to control it. If you're doing it yourself, it can be done with Python or something similar. And typically it will be higher cost than just a handheld probe, but it will give you better results. Let's talk about, sorry, this is example of our near field probe solution. What we try to do to mitigate the issues from the previous slide is essentially integrate the probe with the camera and with our software. So now we're trying to improve the repeatability of these probes because now with the camera and software, we can track the movement of the probe and we can make a lot of measurements and we can stitch the measurements to the live video stream. So we maintain the low cost of handheld probe, but we're trying to improve it a bit. We're adding real-time tracking, we're adding the software, we're adding high-end spectrum analyzer. So now that tool become a bit more controlled. It gives you a bit more flexibility and much more accuracy. So here are some of the advantages of using slightly more controllable probes. So first of all, flexibility and portability. It's again, small solution, very easy to take with you. A broad frequency range, especially if you're designing these tools yourself, you can either design multiple probes, each one of them suitable for a specific frequency, or with a bit of effort, you can design a wide dynamic range probe to cover the frequency that you need. So you do have some flexibility in the probe design here. Again, the cost, it's still be lower than automated tools, and of course, easy to use. You can see that here with the integration of the video and real-time measurements. Now we're talking about the automated solutions. The automated solutions are kind of the high end of that. Essentially, you can see here the scanner. And where's my mouse? Okay. You can see here the scanner. So the only way to measure the magnetic field is with antenna, right? So either you use a handheld probe with a single probe, or you use something like a scanner, which has 1,248 antennas, 7.5 millimeter apart. So now you can do very repeatable measurements very quickly in a very accurate way. Sorry. So automated near field scanner will provide you higher level of precision, higher level of repeatability. And of course, the resolution is much, much higher than the resolution that you can achieve by hand. Faster testing and efficiency, this is the overall of the process, because the time it takes you to scan the DOT depends on the resolution that you've selected. So native resolution is 7.5 millimeters. That means that every 7.5 millimeters, we are making a real-time measurements. But the highest resolution is sub-millimeters, actually very, very tiny, 0.06 millimeters. So obviously, if you want to scan at that resolution, that will take time. So the time that it takes the scanner to perform the test depends essentially on your setting and on your requirement. Again, since everything is controlled by a software, you can essentially load a lot of different files to help you, starting from visualization tools like or images like pictures or any Gerber files or things like that, overlay them, as you can see here on that picture. We can overlay the measurements on top of them. So that gives you a pretty good understanding of how the system behave. And of course, again, you can integrate any essentially simulation automating software to that and perform the process in a very automated way. This is the portfolio. So we have several types of scanners. This is the EM scanner, and this is the image of the EM scanner. As I mentioned, the native resolution here is 7.5 millimeter. We are using external spectrum analyzer. So if you have a spectrum analyzer in your lab, you don't need to purchase another one. Most of the spectrum analyzer are supported. The scanning area, essentially this area here, is like an A4 page. So you can place your DOT here and start the scan. The key use cases are PCBs and complete products that you can either place on the scanner or place the scanner, attach the scanner to the unit. The next version is the R version. R stands for high resolution, and the maximum resolution of that unit is 0.06 millimeters, so it's less than a human hair, essentially. The scanning area is the same scanning area, and we're using as external spectrum analyzer. The key difference between the EM scanner and the R version is that the R version designed for smaller DUTs, even though the scan area is the same, but scanning the entire area at 0.06 millimeters will probably take a few hours. However, and we had a customer that, for example, made in-ear hearing aids. So the size of that thing is around 7 millimeter. So if you need to test a very small component, like few centimeters, you can definitely increase the resolution. It will take a few minutes, but you will get a very detailed scan in a much higher resolution. Usually 1 millimeter will give you a pretty good indication. Next one is the EM probe. The EM probe is a robotic arm, and we can scale that up to essentially any size. And the idea behind the robotic arm is the ability to trace the topology of your DUT. The scanners are flat, and we expect to get some kind of a flat DUT. You can still put a PCB on or place a PCB on the scanner with some capacitors, but the further away from the scanner, you are losing resolution because the emission spreads, so it will cover more cells. So the recommendation is actually to put the DUT as close as possible to the scanner. But in some cases, you have bulky capacitors or transformers on the PCB. So how to scan that? So for this, you will need to use the EM probe. So essentially, it's a single probe solution that can follow the topology of your DUT. The trade-off here is time. It's still automated, it runs on the same software, but obviously it's a single probe solution. It will take time to scan everything, but you have the advantage of the Z-axis. So again, there's no good and bad here. It more depends on the requirements. NFP kit and the software. So these are our probes. It's a kit of 5 probes based on the frequency range. And again, the idea here is we can track, it comes with a camera, and we can track the movement of the probes, and we can overlay the measurements to the video, to the live video stream. So you will see the emissions coming from the DUT in the real time. And what we're trying to do here is to make this product much more repeatability and accurate than just a handheld probe. Now, all our products can be accessed and controlled by actually any user or any software that you want to write. We're providing the API. However, we do have a software, and I will use our software here, which is the EM Viewer. This version is 2.0. This version this software controls all our products. So you buy the product, and then we have yearly subscription for the software, or you can use your own software or your own script. So we have a technology to essentially measure the behavior of the magnetic field in the close proximity. And the question we're doing, you're using that to measure or characterize PCBs. And the question is, can you do it with antennas? The answer is almost. We do have some version of this product that can measure and characterize antennas. It's completely different. It's the RF scanner. It's another product. We didn't release it yet. We're almost there. We're in the process of calibration. It will take a few months, I believe, but we can adapt, or we're trying to adapt this technology to measure and characterize antennas. The key difference is that while for PCB and EMC application, we characterize the emission power amplitude or power output of the DUT. With the RF scanner, we also, to predict the antenna behavior, we also need to characterize the phase behavior. And that turns to be a bit more challenging than we thought. But we're working on that. So a bit more information about the scanner. This is how it looks like. Oops. This is a GIF, but again, the scan is really fast. The speed of the scan depends on several factors. Most of them related to the spectrum analyzer that you use, the RBW, sweep points, etc. So the wider the range, the more, the higher the RBW and more sweep points, probably it will take more time to scan. So it's a compromise between the features of the spectrum analyzer. The frequency range is up to 8 gigahertz, and the special resolution of the EM scanner is 7.5 millimeter, and we interpolate to half of that. But this is software interpolation. The scanning area, as I mentioned, about A4, and the maximum radiated power, this is the power that we can absorb, is around 40 dBm. This is the high resolution. So high resolution, it's essentially the same technology, so the same frequency range, same scanning area, but the resolution is much higher. Here we are trying to approximate the time. Again, it's a bit difficult to say because it depends on this setting of the spectrum analyzer. But here it gives you some kind of idea of the time it takes to scan at a certain resolution. And the way that we're doing that is essentially we have our native resolution of 7.5, and then we divide that to 8 different levels. So we take every cell and divide every cell by 2 in each axis. So now we can make 4 measurements at the center of each subcell. And then this process repeats itself. So for every level you go up, you're getting 4 times the measurements essentially within a specific cell. And that gives you something like this. So here you can see a 7.5 millimeter scan versus about 1 millimeter, 0.9375 millimeter scan. So we can definitely see that emission is coming out from that component. But if you want to see details, including kind of internal structure, now you need the high resolution. Again, depends on needs. There's no really good and bad. Depends if your DOT is small or if the user is interested in the very fine details of the scan. This is the EM probe. This is the benchtop model. So here you can see we're scanning essentially an LCD screen. And here it's pretty good. The GIF here shows essentially the ability of that solution to follow the topology of something. It's actually can use our probes, or you can use any probe that you want. We're providing the design of this 3D adapter, so you can fit any probe that you want. And the probe that you see here is a beehive probe. And this is the set of the near field probe. So this is exactly how it looks like. We can slowly, I increase the speed of the video a bit here, but you can just slowly wave the probe around the DUT. Spectrum analyzer will make the measurement, and we integrate or overlay the measurements into the live video stream. And then you can manipulate the image to understand exactly where the emission is coming from and to characterize the emission or the DUT. Obviously, to all the probes, we have several types of probes, and they're optimized to the frequency of operation. This is how the probe looks like. You can see this marker. So based on that marker, we know which probe is being used, and there is the RGB dots or circles that allows the software to track the camera. To track the probe. The reason that we're using 3 colors is that we have PCBs in many colors. So we've identified 2 of the colors. That means that the probes, and of course we identify the marker, so we know what's going on. But the board that I'll use today, for example, is red. And we have another board, green, and of course they're blue. So we couldn't find a single color that safely allow us to track the probe. We had to use the 3 colors. Regarding spectrum analyzer, so as I mentioned, we are using external spectrum analyzer. Most likely you have a model that we support, and if not, we have an automated tool to create the drivers. The key requirement is the ability to connect remotely to or control remotely the spectrum analyzer. Most likely with skipping commands, and then you're good to go. But here you can see Ritsu, Keysight, Rode, Signal Hound, Regal, Siglent, many more are being supported. Okay, so I will use here 2 boards, as I mentioned. The first one that already connected is essentially the RFID board, so we will start with them. And you can see here a few things, a few modes of operation. I'll speak about that, and that will explain you a bit of the things that I'm just about to do in the next few minutes. So first of all, we have several modes of operation, and this is actually how a user will usually or typically use the software. The first thing that you will do is kind of a sweep spectral scan. The idea is to do a quick scan and to identify potential frequencies of interest. Here, for example, we can see 13 megahertz, and we can see really big spike here, very wide. So obviously, some of you will recognize that this is actually a DC to DC converter, a switching power supply. So this is a typical noise curve or something like that. So once you identify the frequency that you want to see where it's coming from, you can do a single frequency scan. And that will show you that specific frequency, how it's being distributed across your board. And you can see that here. Then the last thing is essentially combined one. So here you have both the frequency and the special information. The trade-off here is time. A combined sweep takes a bit longer because it's a range, it's not a single frequency, and we keep all the information. Typically, user will do that towards the end of the investigation, just to save all the information for future use. Interleaved scan. So, as I mentioned, magnetic field is a vector. It has a direction. The orientation of the antenna or the probe is very important. So a single scan probably will show you something like that. Now, if you are the designer of the board, or you have the Gerber file or the layout, and you know exactly what's going on, probably it will make sense that this thing here is a complete trace. If not, you need to turn on interleaved mode or to scan that location in 2 different orientation and stitch them together. That will give you a complete picture of that specific trace or any other thing. So interleaved mode is very important to get a full spatial picture or representation of the emission. You can do without it, but again, if it's quick and easy, the recommendation is to use it. Another key problem is something we called intermittent events. You have interference that are kind of coming and going. You can't synchronize them to any other event, non-event, and it's very difficult to capture. The way that we solve that is with something called P-code and continuous scanning. Since scans takes relatively short time, we say just turn on P-code and run it continuously, let it run. Slowly, statistically, we will capture this event and we will start building the emission map of that specific event. A very powerful feature, takes time, it's statistical based, but it works. Eventually, if you have an intermittent phenomena or event that you cannot put your finger on, and sometimes you see it, sometimes you're not, let it run. Eventually, we will capture it. uh, okay. Next thing is to visualize the results. Here you can see it in 3D, but again, if you have all the data, it's very important to know where they're coming from. And the ability to manipulate the view and let the user pinpoint the emission or the problem is, again, very important. Last thing is actually the ability to compare scans. So if you have a product that you know it was working, you know that you passed the tests, scan it. Or if you scan it before and you have the file, now you have a new version, compare the two. Even before going to a chamber or before starting investigation, just by comparing the near field scans, it will give you a pretty good indication if this product will pass or if there's any issue. If this is the old product and then you see something like that, maybe maybe it's better to take another look in this area. And your lab environment. So that's a tricky one because we're recommending or we're promoting this product as a benchtop solution. You don't need to go to a chamber. You don't need a quiet environment. However, we will see things like radio station, 90 megahertz. We do see that 5G emission, Wi-Fi emission around 2.4. So you do see that, but if you know where it's coming from, if you know that you see your 2.4 gig of your router, so you can ignore that. However, if you do want to create a quiet environment, we have a benchtop. There's plenty other companies with a benchtop solution. This is example from EGOS, I think. Yes, it's the EGOS model. So you can easily create an RF quiet environment inside one of these chambers. There is another company that makes RF tents. So again, you can place that on the table. It's not mandatory, but it will help you to get a very quiet response. Again, entirely up to you. Usually, we're not using it. Okay, let's go to the live demo and let's see what we're seeing here. So I'm going to use this board essentially. We have here a power input from here, and we have the DC to DC converter. The switching converter is right here. You can see the coil here. Here we have a 32 megahertz big controller, and then this is the data cable and power cable to the antenna area. The antenna controller is 27 megahertz, and then we have the RFID antenna at 13 megahertz. I just wanted to review that because we will see everything here. I'll skip that just to save time. We all know how much noise power converters cause. So let me just stop sharing and I'll share my screen now, and I'll try to show you guys the software. Okay, so let me turn on the camera so if you will be able to see that as well. Camera. Okay, put the camera on.
Yep.
Yeah, yeah, good. So this is our software. Of course, to prepare to this webinar, I ran few scans. So here you can see the DUT on the board itself. You can see the 3D view. I can play around with the opacity, so you can see the emission from the antenna here. You do see my screen, right? All good. And what you see here is essentially the highest emission. But now I can start selecting area, and let's go to this area here. We have the 32 megahertz clock, and we can see the 32 megahertz clock, how it's being generated here and how it's being distributed. The thing here that we still see 32 megahertz around the antenna area, which not a good thing because that will make its way to the transmission itself. Remember I mentioned the 27 megahertz. So 27 megahertz, you can see that it's being generated right here on the antenna controller area. So you can see it right here. So this is a scan. If we go back to the presentation, so if we go back to here, so this is a scan of the board powered by battery. So switching power supply is not engaged. Let me now switch to the power, to the wall power, and let's run a scan. So let me, and you can see in the camera that we're just doing that line. So let me connect the power from the wall. And now the DC to DC converter should be engaged. Let's go back to the software and run the same scan again. So let's reset everything. Here I'm running the combined scan. So you can see exactly what's going on. This is the 13 megahertz of the antenna, the 27 and 32 megahertz, and all their harmonics. However, if I'll run the scan now, now the DC to DC converter is engaged. So now we see completely different behavior. So we didn't reach the controller area, right? So now we're scanning this area here, the antenna. So the 13 megahertz appears, but you can see all this mountain here is essentially from that area here. The problem with that is that it's obscure any other frequency that we have in the system. Because of this mountain here, you don't really see the behavior of the DUT. And let me, here we're scanning all the way to 210 megahertz, but we can see all the frequencies of interest. So let's wait a minute for this thing, for the scan to finish. I think this is the last row. And then we can start analyzing essentially everything. Okay, so now this is essentially everything. If I'll select the peak here, we can see that the emission is coming from the antenna. We know we expect it. There are more frequencies here that we saw. So again, this is 27, but I need to zoom in a bit. This is the 27 megahertz, 27 megahertz, and we know that it's been generated here. But this one is actually really bothering us, right? So around 124 megahertz. And we can easily see what's going on here. Sorry, we can easily see that it's being generated in this area. But that's not the problem. The problem that if we will keep this frequency, we can see that that frequency also present all the way through the cable to the antenna area. So we can see exactly what's going on in the cable, which frequencies are actually traveling through the cable all the way to our antenna. Now, in this case, it's only RFID, so it's less important. because if there is an error, simply, the card will be read again. But in some critical communication, you cannot afford it, and you need some way to decouple frequencies between different boards. So you can easily see the behavior of that specific circuit here. Now, if I'll go back to the previous scan with the battery, again, same frequencies, same settings, same location. The only difference is it powered by battery or 12 volts from the wall that needs to be converted with a switching power supply. And you can see that the switcher power supply here runs at around 124 megahertz switching frequency. So a lot of information can be obtained from here. Another interesting thing is the harmonics. So you can see when you have a quiet environment, you can see the harmonics and how the harmonics are being distributed across the DUT. So you can see here the 27 megahertz harmonics all the way through the cable to the other side, to the digital control board, essentially. So let me go back to the presentation. Okay, so we analyzed that board. We saw the behavior. We saw the problems of a DC to DC converter. Now we understand what a switching power supply can cause. And these are essentially pictures of the scans. Yes, I'm sorry, any questions?
No.
No. Okay,
so setup. How you are placing that one on the scanner?
How do I place the DUT on the scanner?
Yeah.
Do you see the camera? So it's essentially just on the scanner. Yeah, I just place it on the scanner.
Please zoom out in that one. How to place
Sorry?
into? Could you please elaborate that one, sir?
Maybe move the camera so they can see the whole.
Okay, so just a minute. I need to see the camera. So give me a minute, because I don't see the camera, so I don't know. Okay. Let me try to open the view a bit so you will see that. Oh, that's the maximum. So we need to. Okay, is that better?
Okay, sir, better.
Yeah.
Right, so that's this portion of the scanner. You can see the DUT here. Just placed it on the board, essentially. It's just placed on this corner. That's everything. In the software, I'll show you how it's been done in the software.
Yeah, that is the.
Yeah, so in the software, we can go to the setting, and essentially we can define the location of the board that you want. So you can move it around, or you can play with it, whatever you need. And here it's the cell selection video.
To take, sir. We image need to take and place the software, right?
Yeah, you place the antenna. The easiest way, what we are doing is simply taking a picture, and then we load that to the software.
Okay.
Very easy to do.
Okay.
And you can also load the Gerber files. I don't have it here, but you can new overlay from files, and then we support Gerber files as well.
Gerber file also supported, sir. Yeah.
Yes, at some limit, because Gerber files can be, or Gerber projects can be really complex with high levels. So depends, but simple versions of Gerber files are being supported. So I can see now that we have only about 8 minutes. So I'll just go the next presentation, to the next scan here, and I'll show you that from the things that I did just before the the meeting. But I think it's a bit important to view the examples. So we saw how to characterize the DUT and your traces and everything. And you saw a live scan, so you saw how long it took. But I want to show you a few more things. So this one is actually one of our cards. So we developed that card, and the idea of that card is to measure the phase difference between the cells. This is for the RF scanner for the antenna boards. So initially in the first version, we got some digital noise coming to the RF section. This is the RF section, and this is the digital section. Now, it's barely visible, but you can see here a ground separation and a via fence. But still, we saw digital noise on the RF side. So eventually, we just took the card and scanned it. And then we saw exactly where the digital noise is leaking to the RF side. So very, very straightforward. This is again a few insight about how to decouple power supply noise, or actually any noise. Sometimes the decoupling mechanism is cheap. It's, cost of a ferret, for example, but you immediately get about 20 dB improvement, and easily you can see that. You can see the peak levels. Here it looks the same height, but there is actually about 20 dB difference. Current loop, very, very important. Current loops act as an antenna. Avoid them at any cost. That's one of the key reasons to fail. Here you can see that. You can see how it looks like in an actual implementation, and you can see the difference, the emission levels, and this one is example of how to not to create a current loop. Use ground plane. Don't use dedicated return paths on a single traces. That's not a good practice. Even by mistake, you can create a loop, something like that. You're not paying attention. You connect to component, and this thing is radiating like crazy. A slot in the ground plane, essentially what we did. So there are two key problems with that. First of all, if you have a trace running on top of a slot, that radiates. And second of all, if you want to create or to decouple areas on your board with slots, it's not always working. You can see here that the current goes straight through. So slots, you need to design the slot. Just to make a slot will not help you. It needs to be designed based on the frequency and based on the impedance and material. So you need to pay attention if you are implementing slots in your ground plane. This is a very good example because you expect the current will go around the slot, but it's going straight through. And you can see that it is visible. And again, you can see here the behavior. You can see the level of contribution of the slots to the total emissions. So I think it's around, I don't know, the peak here is probably 25, 26 compared to 45, something like that. So it's easily 20 dB. Decoupling, we spoke about it, very important. Shielding. The best example of the shielding is essentially ventilation holes. If you create a shield around your product, again, ventilation hole needs to be designed based on your frequency if you want to make sure to cool your product. But again, it needs to be a compromise between emission to cooling effect and everything else. And the most important one is to design the ventilation hole based on the frequency of operation. You need to keep that in mind. Shield linkage, not through ventilation hole, many other things. We had a customer that from the US, they replaced the handles. They're making boxes, so they replaced the handles with the pop-up handles, and suddenly they failed the test because emission was leaking through the pop-up handles holes. Ferrets, again, very cheap component, very easy to use, very easy to fit, to essentially create high impedance at a certain frequencies. So it will reduce, improve stability, reduce noise, improve stability of your circuits. So here we have a test circuit that you can change the ferrite and see how they behave. Essentially, it's being used to characterize ferrets before use. Crosstalk at the component level, very important. Here, the example that we give is with deep switches. All the switches are open. So if all the switches are open, why do I see current return here? So there is crosstalk, there is linkage between components, and again, very easy to characterize that with a scanner. This is actually pretty good example of linkage, because if you keep all the switches, and these are physical switches, if you keep them open, you shouldn't see any current flowing back, but you do see it. So again, nothing is certain. Again, we discussed that. Pay a lot of attention to your current path. I think we're kind of out of time, so I'll stop the presentation and open the floor for questions. I just want to measure, to show you, or to speak about one thing, and these are the handheld probes that I showed you, but you showed the video, so I wanted to show you that live, but essentially this is the way it operates. I have can show you some of the probes here in the video. So these are the probes, this how they look like. But I think I don't have time to unplug the scanner and plug the probes. So you will have to believe us on on that or see the video. So I'll stop the presentation now, and I think Cornel, you can open the floor for questions. Yes.
Brilliant.
Thank you very much, Yoram. Okay, so you can unmute now if you would like to ask a question to Yoram, or if you would like him to repeat anything, you can pop it in the chat, or you can just unmute and ask the question.
Everything clear. So it was a great presentation then.
Nothing?
Okay, so we've got one question. Where is it? Can you tell about the ferrite antenna scanning?
About the antenna scanning.
The ferrite antenna scanner.
The ferrite is not related to the antenna scanner. The antenna scanner is a different product. The ferrite is just being used to, essentially ferrite is a resistor at a certain frequency. So if you have harmonics or noise at a certain frequency, which is unwanted, you simply connect, or a ferrite in series at that trace, and the ferrite will dissipate that specific frequency, or the frequency range that the ferrite is designed for. Think about resistor for a specific frequency or specific range of frequencies. That's essentially a ferrite. The antenna scanner is a different product that is being used to characterize antennas. So instead of putting a PCB on the scanner, you will put your antenna, and then we can calculate the antenna efficiency, gain, things like that. But we didn't release it yet, so let's hold that discussion until we will formally release the product.
Okay. Well, if there's no other questions, then how Gerber can be used to check EMC?
So essentially, if you what you saw here, if you load a picture, right, during my presentation, I just used a picture of our board. The picture shows you the top of the scanner, the silk screen, and maybe the top component, but you don't see internal traces. If you will use Gerber file, you can see the entire stack of the PCB, and that will show you everything you need to know. I'll just show you again. I don't have here a Gerber file, but I think I can show you how to load it. So when we are going to the project setting here, we're going to overlay editor. You do see my screen I'm sharing, right?
Yeah.
So here I can load pictures. So these are pictures that I actually took with my phone, and they are in my computer. Then import here, and then the file here is Gerber files, and I can load Gerber files into the scanner, essentially the software. So instead of this, you will have the Gerber file. The entire layout of your PCB will be here. However, I do need to be cautious a bit here. Gerber, there are the simple Gerber, and there are much more complex projects in Gerber. So and sometimes it's also contain information about the layers and the electric, and so usually we're trying to extract the traces only, but sometimes high level Gerber, if they're too complex, the automated tool struggle. We have no issues with Gerber files, which are well designed and fairly simple. But we cannot support all the levels of Gerbers. It's essentially to write Gerber decoders at the project level that it's out of the scope of our products, if it makes sense.
Okay, thank you.
Then we've got another participant who's got his hand up. If you would like to ask a question.
Yeah, my question is about how many layer of PCB it can be work out. Already he has explained maybe it is only going to scan that top layer. If it is a multi-layer board like a 10 layer or 12 layer board, that case layer wise it cannot identify, right?
That's a very good question. So no, we can scan multi-layer boards. The barrier is a ground layer. So we can scan all the layers up to the ground layer. Ground layer will obviously shield all the layers above it. So if you have a ground layer in your PCB, just turn it over, and then we will scan the other side. If you have two ground layers, probably the traces in the middle, the traces between them, probably we will not see them. So that's a very good question. But multiple layers we can see as long as you don't have anything that blocks them.
Yeah, got it. Like it's not depend on the whether it is a digital board or RF board or power supply board, multi-layer board containing all type of modules, right? So that case you are saying if we will remove the ground plane, we can able to trace the thing.
Yes, so essentially, if from electromagnetic perspective, this trace is visible, we will see it. The only reason that it won't be visible is if you have some kind of a shield around it. And then obviously we will not see it, and the ground layer is one of them.
But when we are doing for multi-layer board, obviously ground layer is every layer, below every layer, ground layer will be present. There is no other
Right.
alternative.
Right. I mean, we're using ground layers as well, most likely. So the solution is simply to turn the board over to the other side and scan both sides.
Okay. Yeah. that case, only 2-layer board we can able to do. Though it is multi-layer, only top and bottom we can check. In between, so many tracks, power supply tracks, or digital tracks, or RF tracks are available, then it is not possible.
We can scan, or we can see all the way to the ground layer. It doesn't matter how many layers. We will
Okay.
capture multiple layers.
Yeah.
So if you don't, if you have, we have boards here that are 14 layers. And we can see all the traces. So it doesn't matter. The number of layers is not important. What's important is the location of the ground layer. We will see, if you have a complete ground layer, we will see all the way to the ground layer.
Okay. Fine. Thank you.
Okay, right. So I think we're going to leave it there. We do have a question about cost. So I'll just answer that and say that we will send you detailed information about the costs of the scanners that we have presented here today. So Innovate Electronics will deal with that side of the things. We will send you a copy of this recording if you would like to then come back to us or Innovate with any further questions. Please do so. But I would just like to say thank you very much for joining, Yoram. Thank you for doing the presentation. And yes, we hope to speak to all of you very soon. And like I said, we are open for any questions. Just let us know either through Innovate or directly to ourselves. So thank you very much. Have a great day. And hopefully we'll talk to all of you very soon. Thank you. Bye-bye.
Thank you so much. My name is Nanda Kumar. I am from Innovate Electronics. So our team is based in Bangalore as well Hyderabad. If we have any questions or queries, you can reach out to us and we'll be at your service in any regard. However,
Thank you very much, Nanda.
thank you, Cornel. Thank you, Rom. Thanks everyone for coming and giving a time to understand this technology. Thank you.
Thank you.
Perfect. Thank you. Have a lovely day. Bye.